Attack on Titan excels in many areas, but how does it hold up to science? Today we're turning our attention to the Titans, and in particular the mysterious steam which radiates from their bodies. While this element contributes to the show's atmosphere both literally and figuratively, it's not just there because it looks cool. In this video we'll dive into the science of the Titans and explore why they might actually be more scientifically plausible than you would think. Titans are enormous humanoid beings found in the world of Attack on Titan, known for their towering figures, regenerative abilities, and insatiable appetite for human flesh. But could creatures of such colossal size actually exist within the confines of biology and physics? First, let's consider the challenges faced by large mammals in the real world. As animals increase in size, they encounter a host of physiological issues that make sustaining such mass increasingly difficult. One key concept here is the square cube law, which explains how an object's volume and surface area change as its size scales up or down. Simply put, as an object grows in size, its volume, and therefore its mass, increases faster than its surface area. Mathematically speaking, if you scale up an animal by a factor of L, its surface area scales by L squared, while its volume scales by L cubed. This disproportionate scaling has significant implications for any giant creature. The increased volume means more mass to support, meaning stronger bones and muscles are required. But with relatively less surface area, dissipating heat becomes a major problem. Larger animals generate more internal heat due to their greater volume, but have proportionately less surface area to release that heat into the environment. The largest land mammals, like elephants, have evolved specific adaptations to manage heat, such as large ears that act as radiators. Interestingly, this relationship between size and heat retention is observed in what's known as Bergmann's rule. According to this principle, animal species in colder climates tend to be larger than their counterparts in warmer regions. Larger bodies have a smaller surface area relative to their volume, which means they lose heat more slowly. Conversely, smaller animals with a large surface area relative to their volume can dissipate heat more efficiently, which is beneficial in hotter climates. Now, let's scale this up to the size of a Titan. For simplicity, we'll assume the average human is about 2 meters tall, and a typical Titan is around 15 meters tall. The Colossus Titan takes us to another level. Standing at a towering 60 meters, the Colossus is 4 times taller than a typical Titan. Applying the square cube law, a regular Titan's volume would be 420 times greater than a human's. Its surface area, however, would only be 56 times greater. This means a Titan would generate over 400 times the heat of a human body, but only have about 56 times the surface area to release it. This discrepancy poses a serious thermal regulation problem. The Titan's massive body would produce enormous amounts of metabolic heat, risking internal temperatures that could quite literally cook their own flesh. In fact, mammals use about 10 times more energy than reptiles of the same size, making it even harder for them to grow larger without overheating. This is actually why many dinosaurs were able to sustain such large bodies. So how did the Titans deal with this issue? All of a sudden, our Titan steam starts to look a whole lot less far-fetched. By heating and releasing water in and around their bodies, they could effectively dissipate large amounts of heat. When water evaporates, it absorbs a significant amount of heat energy from its surroundings. Here, the Titan's skin is represented by a layer of particles at the bottom of the screen, appearing red to signify their high temperature. Above this, a layer of blue moisture particles indicates water in and around the Titan's skin. We see the heat being transferred from the skin to the moisture, causing the latter to change colour and rise as steam. By continuously evaporating water in and around their flesh, the Titans could shed excess heat generated by their massive bodies. This would explain the constant emission of steam, especially during periods of high activity or rapid regeneration, when, get this, metabolic rates and therefore heat production would be even higher. Taking a look now at the Colossus, the picture grows clearer. Using the square cube law again, its volume and heat generation would be 64 times greater than that of a 15-meter Titan, necessitating a continuous release of steam to avoid catastrophic overheating. This perpetual steaming not only serves as a cooling mechanism, but also makes it look super cool and imposing. So, while the existence of Titans might appear to stretch the boundaries of biological plausibility, incorporating the concept of evaporative cooling through steam emission provides a scientifically grounded explanation for their thermal regulation. We can rationalize the steaming Titans as a necessary adaptation for managing their internal temperatures. So the next time you see a Titan enveloped in steam, just remember that he's really just a chill guy who gets a bit hot sometimes. If you enjoyed this video and want to see more content like this, make sure to subscribe and check out the links in the description. Let me know in the comments what you think about this scientific take on the Titans and if you have any other suggestions.